Hi, my name is Malia Santos, and today I'm going to be talking to you about some of my results from my dissertation on the phylogenomics and biogeography of the coffee alliance, with an emphasis in Triclicia. Before I begin, I want to thank and acknowledge my two co-authors, Elmar Robrick, who's at the Botanic Garden Mize, and David Tank, who's my advisor. Before we begin, I want to pose a question that I think is really important in phylogenomics, and one question that really drives the research that I do, which is what influences speciation? Big question. Uh, Specifically, asking this question in the African tropics is pretty cool because Africa is normally considered the odd man out when looking at the species diversification, or sorry, species diversity, in comparison to the neotropics and the Asian paleotropics. And so there have been a lot of hypotheses regarding Africa's diversification. And these are not specific to Africa either. They're just two that are really important because of Africa's climatic history, which we'll get into later. And so one of the questions, or sorry, hypotheses that I'm going to be talking to you about today is the fragmentation refugia hypothesis, where we start with one species denoted by the purple leaves in one habitat denoted by this green circle. And in this habitat, the species can interchange genes freely. However, over time, this habitat may become fragmented, in which case genetic drift would be the sole cause of diversification in this group over time. And so as we can see, if those two populations or habitats come back together, we see a speciation event. The second hypothesis is the ecotone hypothesis. The difference between these two is, rather than being in a continuous habitat, the species resides in a transition zone or an ecotone between two habitats. And so you can see here we have one species residing on more of the green habitat and one individual residing in the green habitat and one individual residing in this orangey yellow habitat. In this scenario, we still have genes being able to interchange freely. However, over time, we see a decrease, or we can expect there to be a decrease in gene flow because of selection based on the habitats. And then over time, because of that selection, we can see, again, a speciation event. And so I'm going to come back to these after I present my results. But I want you to keep these in the back of your mind. And so before we dive into the nitty gritty of everything, I'm going to introduce my study species. So the Coffee Alliance is a big speciose group in Rubiaceae. It's a clade of an informal clade of about 10 tribes, 90 genera, and about 2,000 species. And I'm showing you this because in order to date our tree, we took samples from all of these different tribes. I do want to point out that my study genus, Triclicia, resides in the Coffee tribe, and so not to be confused with the alliance. So getting into Triclicia is a genus of shrubs or small trees that are located throughout sub-Saharan Africa. They're architecturally very similar to coffee, and most of the morphological / biogeographic work done in this group was done by our co-author Elmar Robrick, who published a series of monographs looking at these morphological / biogeographic traits. The traits, I'm not going to spend too much time on the morphological traits today because I want to show you some of my more biogeographical results, but take my word for it that the traits separating the species in this genus are normally very minor and very continuous. And so our objectives became twofold. We wanted to provide a phylogenetic context for the evolution of morphological traits set out by Elmar. And two, we wanted to provide a temporal framework for the origin of triclicia in order to infer any biogeographic history throughout Africa. And so from here on out, I'm going to present to you the methods and then the results for each of the objectives I list here. And so for the first objective, we collected herbarium tissue from 53 triclicia species. We used the Angiosperm 353 bait kit to target 353 putatively single copulosi. We used Tide Piper to process our reads. I do want to point out that we used the Mickley et al. 2020 or the Mega 353 target file to add in more Rubiaceae samples to that target file to improve the capture efficiency that we were getting. And we also used IQ-Tree to create gene trees and Astral3 to estimate a species tree. And so the next thing I'm going to show you is our best hypothesis for the relationships in triclicia based on the data that we had. And so this is our Astral3 tree. It has about 320 genes, and so we did have to drop a few. But first I wanted to point out a few things on this tree because I know it might be a little small, you might not be able to see it. But the red dots that you're seeing on the nodes are local posterior probabilities that are lower than 80%. And the red stars next to the local posterior probabilities or nodes are cases in which the null hypothesis of a polytomy cannot be rejected. And so we do still have some uncertainty in our tree. However, it's much better than what we were seeing before. One thing that I really want to point out here is this first column on the right-hand side of the tree, which is indicating the previous taxonomic sections of the group. And so it's sectioned out by color and also by the name. But what you can hopefully see is that there's not a lot of monophyly in these sections. And instead, we're seeing more of a geographic split between the Guinea-Congolian or the West African region and the Zambesian or East African region. And so broadly, morphology is not explaining the patterns of speciation that we're seeing. And so this led us to ask, well, if it's not morphology, did past climatic fluctuations cause the patterns of species diversity that we see today? And so here's a graph of the global climate change and major tectonic events. I'm really just showing you this to indicate that things have changed. And here is where we think the coffee alliance originated, and here's where triclicia originated. Before we get into this, I do want to go over some of the historical climate changes in tropical Africa because you may not be aware of it. But in the Miocene, we had this colder and drier climate denoted by my cold emoji face. And then as we transition into the late Miocene, we have a renewal of warmer and wetter climates, as denoted by my hot emoji face. And this renewal of warmer and wetter climates extends all the way into basically the mid-Pliocene, which is normally or sometimes referred to as the Golden Age, where tropical forests have re-expanded. And as shown here in this first figure, have re-expanded and are continuous across the continent of Africa, as denoted by that gray area. As we get into the late Pliocene, we have a transition to a cooler climate again. And then with the Pleistocene, we get glacial cycles that are caused by, that cause climatic fluctuations pretty rapidly. And so in these Pleistocene glacial cycles, we can see three major aridity events that happened, which caused those drier and cooler climates. And during the drier and colder climates, we're seeing a contraction of the rainforests again. And so we come from this big expanded area into multiple little refugee areas, if you want to consider them refuges. In those hotter areas, we do see again that the forests re-expand, reconnect, and so this happened many, many times during the Pleistocene. Okay, so going into some of the methods for the second objective, to be able to provide a temporal framework for our phylogeny, we needed to date our tree. And so in order to do that, we had to take samples outside of Trichlycia. And we did this by taking samples from the open access Kew Tree of Life Explorer and Antonelli et al. 2021, which was a phylogenetic or a study done on the tree of Gentianales. And before I go on, I just want to kind of plug this Kew Tree of Life Explorer because I think it's really cool and a really great resource. The Kew has gone through and data mined basically all of the angiosperm 353 data that's been published so far, and along with data mining genomes and transcriptomes for those 353 genes in order to have it all in one place, one free downloadable place. And so this is a great way to use data that is already out there. Okay, so in order to date our tree, we used BEAST with a relaxed log normal clock, and we used the secondary calibrations from Wickstrom et al., which was the time tree of asterids. However, I do want to note that they did use fossils, and so even though we're using secondary calibrations, it's still from fossil data. And then we did the ancestral biogeographic analysis in RevBase. And so our results for this are, or our first result is the coffee dating analysis. And so what I'm really just trying to show you here is that the secondary calibration points that we used from Wickstrom et al. 2015 span the backbone of our tree. The dates that we collected are very similar to those that we've seen before. I'm not going to spend a lot of time on this tree, but please email me if you have any questions or you want to know more about this. I do again want to note that all of the colored areas are our coffee alliance, along with our tribe coffee down here, which houses Trichlycia. Our next result, which I'm going to spend a little bit more time on, is our ancestral biogeography analysis using RevBase. So before we begin, I just want to point out some things on this tree. And so the colors that you see here are corresponding to different areas in Africa. We coded these areas based on Elmar Roderick's monographs that he wrote, and basically any herbarium data. And so we chose 5 regions, and I've also put lines in for those major aridification events that cause the fragmentation of the rainforests. And so what we can see, if we are now looking at the tree, is that we have in the origin of Trichlycia originated in the Guinea-Congolian region, or West Africa, which was proposed by Elmar. We also see that the majority of the diversification events are happening in this hotter, or in the Pliocene, in this hotter renewal of warmer climate area. So things are re-expanding, they're coming back together. We also can see that we have one transition to Madagascar, and we can also see that same sort of split between the Guinea-Congolian or West African region and the East African Zambesian region. I do also want to point out, I wanted to point it out before, but this tree is only based on 38 genes, and so we did lose a little bit of our information, and we did lose some taxa, and so this is a smaller tree than the tree that I showed you previously. Other than that, what I also wanted to say, or bring it back to the two hypotheses that I brought up before. And even though I really wanted to specifically say one that like one hypothesis was more prevalent in the speciation events than the other, I really think that both are probably playing a role here. And so in this fragmentation refugia hypothesis, we have speciation happening right after a fragmentation event. So these little lines here in the same habitat. And so they didn't diversify into different habitats. And so that's kind of pointing towards this fragmentation refugia hypothesis. In the ecotone hypothesis, we do see some transitions into the drier Zambesian East African region from the wetter West African Guinea Congolian region. And so that is providing us some evidence that there was selection based on the ecotones, or sorry, the habitats, and that also might be a cause of speciation. So some of our conclusions are that Trichlicia originated in that Guinea-Congolian region, and that we see a retention of morphological ancestral polymorphisms, which is basically just saying we didn't see a lot of monophyly in those morphological traits. And the geography, along with climatic fluctuations in the Pliocene, seem to play a role in diversification. I'd like to acknowledge my colleagues that helped me put this talk together / listen to it a lot of times, and the botanical gardens that it gave me my herbarium samples, along with the universities in which I've done this work.